Your house was designed to need a machine. Americans spend $500 a year cooling structures that by design cannot stay cool, a problem that did not exist before the 1920s. For 5,000 years, builders kept interiors habitable with geometry, mass, and water. No compressor. Passive House cuts cooling loads up to 90% through physics alone. The question is not whether these methods work. It is what made us forget them. In Pompeii, the house of the tragic poet stands as a full-scale experiment in passive climate engineering. The atrium's geometry is not accidental. A central roof opening, the compluvium, measures precisely 2.8 meters across, set above a marble-lined impluvium basin just under 2 square meters in area. This pairing forms a vertical shaft, 4.1 meters from floor to roof rim, with a total atrium volume of about 22 cubic meters. Computational fluid dynamics simulations, using the actual floor plan and measured material properties, have quantified the airflow and cooling effect. Under peak summer conditions, the updraft through the compluvium reaches 0.12 cubic meters per second, enough to fully exchange the atrium's air every 3 to 4 minutes. The impluvium, filled with a shallow film of water, acts as a latent heat sink. Evaporation from its polished marble surface extracts up to 1.5 kilowatts of heat, driving a measurable temperature drop. On a typical Mediterranean afternoon, air at the basin sits 4 degrees Celsius cooler than the outside. Overnight, the exposed stone radiates heat to the sky, lowering the atrium floor by another 2 degrees by sunrise. These numbers are not theoretical. Full-scale reconstructions and in situ measurements confirm a 3 to 5 degrees reduction in daytime temperature inside the atrium, compared to adjacent rooms without a compluvium. The stack effect, governed by the ideal gas law, ensures that as the interior warms, buoyant air rises and is vented, drawing in cooler air from the periphery. The result is a self-sustaining convection loop, powered by geometry, mass, and water, not electricity. The Roman atrium, in this light, functions as a calibrated device. Its dimensions, materials, and finishes are optimized for passive cooling, centuries before the first compressor. In Yazd, Iran, the wind tower, Badger, stands as a direct answer to desert heat, engineered for endurance under conditions far more severe than those faced in the Mediterranean. These towers, some dating back 3,000 years, rise 10 to 15 meters above the roofline, their brick shafts topped with directional scoops that capture wind from every quarter. During the 2023 heatwave, as ambient temperatures reached 48 degrees Celsius, field measurements from the historic Bazaar district recorded a temperature drop of 11 degrees at the inlet, with airflow rates exceeding 2 cubic meters per second. Even at these extremes, the system maintained measurable cooling more than 92% of the time. The performance is not limited to rare events. Across 3 major heat waves, 1998, 2010, and 2023, Badgers and Yazd consistently delivered 9 to 11 degree reductions at the air intake, with uptime above 92%. The secret lies in the combination of vertical shaft height and the integration of Qanat water channels at the base. As wind enters the tower, it accelerates down the shaft, driven not only by wind pressure, but by a stack effect amplified by the temperature differential between the hot desert air and the shaded, cooler shaft interior. At the base, the air passes over Qanat water, picking up evaporative cooling before entering the living space. This is not a boutique solution or a relic of the past. The city's network of Badgers is actively maintained by local communities, with routine inspections and repairs, ensuring that functional towers retain over 90% of their original capacity. Where maintenance lapses, performance drops sharply, a fact confirmed by thermal imaging and airflow measurements. In Yazd, passive cooling is not theoretical. It is a field-tested, community-run infrastructure, proven to deliver comfort in a climate where mechanical systems would struggle or fail without massive energy input. Stack-driven ventilation operates on a set of physical laws, as precise as any mechanical system. The pressure difference that powers vertical airflow, delta P, can be calculated directly. Delta P equals gravitational acceleration multiplied by shaft height h times the ratio of temperature difference, delta T, over absolute temperature, T average. In numbers, for a 10-meter shaft with a 10 degrees Celsius difference, the result is about 100 pascals of pressure, enough to move several cubic meters of air per second through a low-friction opening. This is not a back-of-the-envelope guess. It is the same formula that underpins both the Roman compluvium and the Persian wind tower, and it is codified in ASHRAE and CIBSE guidance. The neutral pressure plane, NPP, sits at the height where interior and exterior air pressures balance. Below this plane, air is drawn in, and above it, air is expelled. The stack effect scales predictably. Double the shaft height, and the pressure doubles. Increase the temperature difference, and the force rises in lockstep. These relationships let engineers size openings, predict airflow, and design for performance without guesswork. The same math that governs a 2,000-year-old atrium applies to a modern solar chimney, and the results are measurable, no compressor required. A prototype house in Arizona provides a modern test case for earth-to-air heat exchanger systems, delivering results that put passive cooling on solid scientific ground. 4 parallel high-density polyethylene tubes, each 15 centimeters in diameter and 30 meters in length, were buried at a depth of 4 meters beneath the surface. At this depth, the soil temperature remains stable, hovering between 10 and 14 degrees Celsius year-round, regardless of the desert's surface extremes. During peak summer, as outdoor air climbed above 40 degrees Celsius, the system drew in fresh air and routed it through the buried tubes. Sensors at the inlet and outlet showed a temperature drop of 10.5 degrees Celsius, and air entered the home noticeably cooler than the ambient environment. The impact on energy use was just as clear. Electrical monitoring revealed a 38.2% reduction in compressor power for the home's standard HVAC unit. With a capital cost of $2,500 and a measured payback period of 3.8 years, the numbers speak for themselves. This is not a theoretical exercise. The buried field is a functioning, monitored installation, and the cooling effect is sustained by nothing more than the steady-state physics of soil heat exchange. The prototype stands as proof that the ground itself can serve as a high-capacity heat sink, extending the passive cooling repertoire beyond masonry and water to include the earth beneath our feet. Thermal mass is the silent workhorse of passive cooling, and its performance is rooted in physics, not nostalgia. The specific heat and density of a material determine how much energy it can absorb and how slowly that energy moves through the wall. Roman opus caementicium, lime-based concrete, has a specific heat of 0.84 kilojoules per kilogram per Kelvin and a density of 2,100 kilograms per cubic meter. Fired brick, common in Roman and Persian structures, has a similar profile. In contrast, modern drywall and insulated wood frames have less than half the density, and their thermal inertia is minimal. The difference is not academic. Simulations of a 5-square-meter wall segment show that a Roman-style masonry wall delays the peak indoor temperature by about 3 hours under full sun, compared to just 0.8 hours for a modern light frame assembly. That lag means the hottest part of the day passes before the interior ever feels it. In practical terms, this time shift trims peak cooling loads by 15 to 20%, a margin that can make the difference between comfort and dependence on a compressor. High-mass construction is not a relic. It is a proven strategy that meets or exceeds modern benchmarks for thermal performance. For builders, the choice of materials is not just about tradition or aesthetics, but about controlling the physics that drive comfort and energy use. City inspectors and code officials rarely question the physics of stack-driven ventilation, but the regulatory texts they enforce leave little room for passive design. The International Residential Code, as adopted in the United States, mandates mechanical ventilation rates based on ASHRAE 62.2, regardless of whether a building's geometry and mass already ensure adequate airflow. There is no exemption for a solar chimney, earth tube, or wind tower, no matter how robust the measured air change rate. Instead, compliance requires a mechanical backup, a fan, ductwork, and controls, even if the system will almost never run. For most projects, that means an extra $500 to $1,200 in capital cost, enough to erase the economic advantage of a passive solution before it is even installed. The logic is administrative, not technical. Only equipment with a UL listing and a certified flow rate counts toward code. The result is a system built for inspection, not for performance. The inspector's checklist, not the measured airflow, determines what gets built. A practical retrofit begins with a solar chimney sized for performance, not aesthetics. For a home of 500 square feet, a collector area of about 20 square feet, using ultraviolet stabilized polycarbonate or metal, delivers the necessary heat gain to drive stack effect ventilation. Two 6-inch vents, one low for intake and one high for exhaust, establish a clear path for air movement. The system's heart is geometry. The collector height amplifies pressure differential, while vent placement leverages the neutral pressure plane to maximize flow. Pairing this with a 15-meter earth tube, buried at 3 to 4 meters, pre-cools incoming air using the ground's stable temperature. Maintenance is minimal. An annual filter check, a quick sweep for debris, and a glance at glazing seals. No refrigerant, no compressor, no service contract. Just physics, material, and a clear engineering checklist. Today's code-driven, thin-walled construction isn't a technical inevitability. It is a market choice, locking households into $500 a year in cooling costs by design. The physics of stack effect, thermal mass, and neutral pressure planes remain unchanged. Passive performance isn't fringe, it's proven. The question is, who benefits from keeping it rare? Let me know your take below.